Hi Year 13. This lesson we will consider the final method for working out the enthalpy change of a reaction. Now this final method involves energy cycles, and the very fact that we're using energy cycles depends on this first law of thermodynamics. Now this states that energy is always conserved, it cannot be created or destroyed, but it can be converted from one form into another. Now the reason that we would use this law and we would use it to draw an energy cycle is because some reactions are explosive or toxic and it's very difficult to measure their enthalpy change directly in the lab. A couple of examples would be the delta HF of nitroglycerine. Well, it's explosive, very difficult to measure in the lab. Again, hydrogen cyanide is toxic, so the delta HF wouldn't be something that we would want to measure in the lab. So therefore we use these energy cycles and we use them with reactions that we already know the enthalpy change for to measure these, to calculate, I should say, these enthalpy changes of these more tricky reactions. Now the fact that we can draw these energy cycles and we can use them to measure the enthalpy indirectly depends on Hess's law. Now Hess's law states that the enthalpy change for a reaction is independent of the route taken, provided the initial and final conditions are the same. Now if we look at the cycle on the screen, and again you've got it in your notes. Now if we label up the first reaction from reactants to products 2 as having the enthalpy change delta H1. Now there is the direct route from the reactants to the products 2 that we want. Now if this reaction were tricky to measure, we could use these other two enthalpy changes to measure this tricky one. So we could go via a second law of products 1. So reactants to products 1 has the enthalpy change delta H2. From products 1 to products 2, it has the enthalpy change delta H3. Now according to Hess, delta H1 will be equal to the sum of delta H2 and delta H3. So we're still ending up with products 2, but we're just getting them in two slightly different routes. Now our energy cycles that we're going to draw will look just now. On page 42, you've got a reminder there about the delta HF. Now remember that delta HF is the enthalpy change when 1 mole, and that 1 mole is really important. It's the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states under standard conditions. Now elements don't need to be formed, so therefore by definition the delta HF of any element will be 0. Now if we look at the first example, we're asked to work out the enthalpy of reaction for the thermal decomposition of calcium carbonate using the enthalpies of formation provided in the table. So we want to work out this delta HR. Now it's not a definition that we have to learn, but it's just the enthalpy change for this reaction, which is a decomposition reaction. Now you can see that you're given some information in the question. We are given a little table, and in that little table we have got the delta HF values for calcium carbonate, for calcium oxide and for carbon dioxide. Now all these compounds appear in the equation for the reactions whose enthalpy change we want to calculate. Now we're going to write out the 3 equations just to remind ourselves of these equations for the delta HF. So for the delta HF of calcium carbonate, I'm going to need calcium atoms reacting with carbon atoms, reacting with oxygen molecules to form 1 mole, and remember it's got to be 1 mole of this calcium carbonate. Now I've got to keep the state symbols there. There's a solid, an S there for solid, but I've got to keep the balancing right. So you can see that I've got 3 atoms of oxygen in this calcium carbonate, so therefore I need 1.5 molecules. I'm going to do the same for calcium oxide. So calcium atoms will react with oxygen molecules to form calcium oxide. And again, I've got to keep the balancing right, and by definition I've got to have 1 mole of calcium oxide, so therefore I only need half a molecule of oxygen. I'm going to do the same for carbon dioxide. So 1 mole of carbon will react with oxygen to form carbon dioxide, and it's a gas. Now I want to take these 3 equations that I have just written and I want to get them into a cycle to measure this delta HR. Now if I look, I've got calcium carbonate on the left hand side. Now I'm going to list down here, and this will form the bottom of our cycle, all the atoms in calcium carbonate. And I'm using this delta HF equation that I have just written, the blue one, to help me out with that. So these 3 reactants, its constituent elements, will go together to form a mole of calcium carbonate, and this black arrow that I have just drawn will show the delta HF for calcium carbonate. Now if I look at the products, I've got calcium oxide, but again in the bottom line I've got its constituent elements. So 1 calcium and 1 of those oxygen atoms will form calcium oxide, and this black arrow will be the delta HF for calcium oxide, and I should label that as calcium carbonate. Now left over on the bottom line, after forming calcium oxide, I have got the elements needed to form carbon dioxide, and the black arrow that I have just drawn is the delta HF for carbon dioxide. Now I'm going to use Hess's law, and I'm going to use the 2 routes that I could take, 1 direct and 1 indirect, and we are going to use it to work out this delta HR. Now there is our direct route from calcium carbonate to calcium oxide and carbon dioxide, and here is our indirect route. Now Hess's law states that our direct route will be equal to the sum of our indirect routes. So delta HR is going to be equal to. Now take care to look at the cycle that we've drawn really carefully, and in particular the direction of the arrows. Now if I look at my yellow arrow again, this yellow arrow is going against the direction of the black arrow. So anywhere I go against the direction, I've got to put a minus sign in front of. So it's going to be minus or negative the delta HF of this calcium carbonate. Now as I complete my cycle, my yellow arrow now is going in the same direction as these last 2 black arrows. So I don't need to put a negative sign on. I'm going to add to that the delta HF of calcium oxide and the delta HF of carbon dioxide. Now I'm going to use the values that the question gave me. So if I go and I solve that then, we're going to have negative minus 1207 plus minus 635 plus minus 394. Now I'm going to solve it. A minus times a minus is a positive, so that's going to end up as 1207 minus 635 minus 394. When I plug that all into the calculator then, that will come out with a value of 178 kilojoules per mole. Now this is an endothermic answer, and that makes sense because the decomposition of calcium carbonate will require heat energy. It will absorb that heat energy, hence we know that decomposition is an endothermic reaction. Now you've got space at the top of page 43 to write in your working, and you will see that it's really important to show this working because in your exam you will get marks for the working out, and then you'll get an extra mark at the end for the correct answer. So this working out is really important. Let's look at another example. Let's look at example 2 on page 43. So this time we're asked to use the enthalpies of formation to calculate the enthalpy change for the following reaction. Now again, this is just the enthalpy change of any reaction, delta HR. Now if you look at the information that we're given the delta HF value for 1 mole of water and for 1 mole of iron oxide. Now if we just remind ourselves about these equations. So in order to form water, we are going to need hydrogen atoms, a molecule of hydrogen, reacting with half a molecule of oxygen to form 1 mole of water. And if you notice, this is water in its gaseous form. Then for iron oxide, we're going to need 3 moles of iron reacting with 2 molecules of oxygen to form 1 mole of iron oxide, Fe3O4, and this is a solid. And we're given the enthalpy change values for both these reactions. Now we've got to use them, and we've got to put them into a cycle in the same manner as we put them into a cycle for example 1. Now if we look at iron, well, iron's an element, it won't have a delta HF value, and the fact that it is an element means that we don't need to form it. Now we do need to go and we do need to form water. So if we look really carefully at the equation, we have got 4 molecules of water. So actually it's going to be 4 times the delta HF value. I'm going to need 4 hydrogens. And I'm going to need 2 oxygens. Now together they will react, but this will be 4 times the delta HF this time of water, because in the equation we have got 4 molecules of water. Now again, hydrogen is an element, we don't need to form it, but we do need to finish off by forming iron oxide. Now there's only 1 mole of this iron oxide. So what I need to add to my bottom line then is I need to add 3 iron atoms. Now these 3 iron atoms and 4 oxygen atoms will react together to form iron oxide. So I have got here the delta HF for this iron oxide. Now I'm going to solve it in the same manner that we used for example 1. So here is the direct route, here's the indirect route, and I'm taking into account whether I'm going with the direction of the black arrow or whether I'm going against the direction of the black arrow. So our delta HR this time is going to be equal to, now I'm going against the direction of the arrow, so it's going to be negative 4 delta HFs for water. Then I'm going with the direction of the arrow for the formation of iron oxide, so I'm going to add to that the delta HF for iron oxide. Now if I pop in the values then, so it'll be negative 4 times, and the delta HF for water is minus 242. You're given that in the question. Add it to the delta HF for iron oxide, which is minus 1117. Now when we solve that, a minus times a minus becomes a positive. And the final answer then will work out at minus 149 kilojoules per mole. So this reaction is an exothermic reaction. And we've got to remember the fact that the delta HF for an element is 0. You have a possible short. I'm going to do one more example together because this time you're not given the equation, this time you're asked to write the equation. So number 2 asks you to calculate the enthalpy of combustion of propanone, and you're given this information. Now if we look at the question, we always take the reaction that we want to find, and like we've done in example 1 and 2, we pop it at the top of the cycle. So the enthalpy of combustion of propanone. Now propanone is a ketone, and we will study ketones next year, but for now you're given its formula. We're going to burn it, so that's always plus oxygen. We're going to form carbon dioxide, and we're going to form water. Now it's important to burn 1 mole of it, but it's also important to get your equation balanced. So I'm going to need a 3 there to get the carbons balanced, and I'm going to need a 3 there to get the hydrogens balanced, and then I'm going to look at the oxygens. So we have got, I'm going to need a 4 there to get the oxygens balanced, and we're going to finish off that equation by popping in the state symbols. Now this time we are given delta HC values, and we are given a delta HF value. Now we will in another lesson learn how to deal with delta HC values, but there's just a little fact that we have got to realise. Now the delta HC is for hydrogen. So if we were to burn 1 mole of hydrogen, so plus oxygen, we would form 1 mole of water, and I would just need half that oxygen molecule. So therefore it's important to realise that this delta HC for hydrogen is in fact the same as the delta HF for water, and it's important to realise that. Now again, if we look at the delta HC for carbon, this carbon is burning in oxygen to form 1 mole of carbon dioxide. And it's important to realise that the delta HC for carbon is the same as the delta HF for carbon dioxide. So really we have got 3 delta HF values that we're going to use. Now we want to work out this delta HC. And again, we have got to form this cycle. Okay, so the first one that we're going to take is this propanone. We're going to think of the elements that make it up. I haven't written out the equation for the delta HF, but probably we don't need to this time. We have got 2 carbons. We have got 3 hydrogens. That should have been 3 carbons, my apologies. We have got 3 hydrogen molecules, and we have got half a molecule of oxygen. Now those are the constituent elements that are needed to make up propanone. Now all together, those elements will react together, they'll form propanone, so this first arrow is the delta HF for this propanone. We don't need to form oxygen because it's an element. Then we can use 3 carbons and 6 oxygens to form 3 carbon dioxides. So we've got 3 times the delta HF of carbon dioxide. Then we have got 3 times the delta HF of water. And just to keep everything strictly speaking correct, we will actually have 9 molecules of oxygen. So we will have, or 9 atoms of oxygen, sorry. We will have a total of 4.5 molecules, so that we have enough oxygen to make propanone, and we have enough oxygen then to make the carbon dioxides and the hydrogens. Now we're going to use this cycle. So the yellow arrows, there is our directorate, there is our indirectorate. And we've got to be very careful and look carefully at the directions of these arrows as we solve. So the delta HC, what we're trying to find, will be equal to. Now we're going against the direction of the black arrow, so it's going to be negative the delta HF of propanone. We're going with the arrow this time, so it will be plus 3 times the delta HF of carbon dioxide. And be careful, you've got your 3 in there because we're forming 3 moles of it. Plus 3 times the delta HF of water. Now we've got to use the numbers that we're given and we've got to solve it for this delta HC. So it is negative minus 217 plus 3 times minus 393 plus 3 times minus 286. Now this will end up as 217 minus 1179 minus 858. And when we plug that into the calculator, we'll find then that our final answer is minus 1820. It's a combustion reaction, and we would expect a combustion reaction to be exothermic. But if you're struggling, and we're still thinking about the reaction that we have just covered. Now I don't recommend this shortcut because it'll be very important in A2 that you're able to draw these energy cycles, and in fact we'll take them a step further to consider Born-Haber cycles. So it is important to invest the time learning how to draw these cycles. But maybe the shortcut can be used as a little check. And this shortcut, providing you're using the enthalpies of formation, is on the screen. So the delta H of the reaction is the sum of the delta H of the products, take away the sum of the delta H of the reactants. Now if we think of the sum of the delta X of the products, so we have got iron oxide as a product, its delta HF was minus 117. Taken away from that, 4 times the delta HF of water, so 4 times minus 242. And if you do that, you'll find that it comes out as the exact same answer that we got from our cycle. But like I say, it's really important that you use the cycles, but the shortcut can be used as a little check that you're correct. Now it's important again that we work through some questions and we make sure that